Hello, I'm Tiffany Trader, HPC Wire Managing Editor, and we're here in Dallas at Supercomputing SC22. And joining me is Nick Dubé, Senior Fellow and Chief Architect at Hewlett-Packard Enterprise. Nick is the lead technical deployment of the Oak Ridge Frontier Supercomputer, a DOE HPE AMD collaboration.
Yeah.
And so we were both at the Top 500 BOF last night. It was really great BOF. And one of the lead key speakers there was Scott Atchley
Yep.
from he's an HP systems engineer at Oak Ridge.
At Oak Ridge.
And I didn't realize until his talk. Oh, I knew some of the details, the behind the scenes details, but this was the most detailed account that I had heard yet of a fascinating talk about the intense period of benchmarking and troubleshooting that led up to the eventual crossing of the Exascale run in May. You know, this heroic effort to get over that XFlop finish line. And what I learned is that you had something of a hero role in this story, going on site, living on site, and developing these power management tools that specifically ended up providing the visibility that led to a critical fix. Scott Atchley said the performance management tool that you designed had amazing resolution beyond the capability. Sorry to flatter you too much, but beyond any capability that they'd had before. So I'd like to hand that off to you to share, what happened and some of those details and what that was like.
So the story on Frontier is actually quite amazing, and it's the first time, it's an Untold story. It's the first time yesterday Scott actually mentioned some pieces of it. Many of us ended up kind of going to Oak Ridge at the end of February, early March, because May was coming fast, and this year the top 500 for ISC was almost a month sooner, because ISC was almost a month sooner than usually it's at the end of June. And bringing Frontier, it's not only the largest system ever built, but it's the first of its class, right? With a brand new fabric at that scale, new infrastructure, new AMD GPU, new software. So there was new on top of new on top of new, and then being the largest one in the world. Well, it sets up for very interesting challenges. But we were basically in a all right, we're throwing everything we have at it. We pulled. I was very fortunate to lead the team. It was amazing, but it was a huge team. We had like over 100 people working on this. We worked on it around the clock. We had people literally working the system around the clock. And it started with getting the infrastructure solid and going. And then what you were talking about, the dashboard, just for a system the size of Frontier, a lot of monitoring tools just don't comprehend a system that has like 40,000 GPUs, because it's so big. The data ingest, just to capture the data, all of the feeds that are coming from the performance of the nodes is massive. So we designed a new tool, and you saw it yesterday at Scott's presentation with a dashboard. Every node in the rack had a colored dot, and we started by what we called greening up the racks, right? And green meant all the nodes were performing individually. And then we blued up the rack, which meant that the rack was performing nominally at the rack level. And then we moved up at the row and then at the system level. We overcame many things. And what people don't realize is that people are like, oh my God, you guys, it's like a miracle that what you guys did. I'm like, no. A system the scale of Frontier is statistically very, very difficult to make and come together and work for an extended period of time without any failure. And people that build smaller systems or are not in our business sometimes don't fully comprehend that.
Absolutely.
But you're like 40,000 GPUs, just the high memory bandwidth, you're looking at 2.4 million memory chips. And for the Limpack run that lasted about 3.5 hours, that means you get zero failure, or whatever failure you get, you have the resiliency put in place that you come on top of it. So that's a pretty amazing accomplishment that the team pulled off. We cut it really tight towards the end, and Scott mentioned that yesterday. We kind of had we called it the sawtooth problem, and it was caused by a default setting in the libfabrics driver, that when we tuned, then the system really performed.
It's an MPI switch.
Yes, it was.
You turned it off.
It's something like. it's an option that actually, if you read the man pages, it tells you this option might, lower performance. But
it's doing all these calls.
it's basically, okay, so in a nutshell, basically the system will run over 20 megawatts when it's running flat out, but we were seeing swings that were like 8 to 10 megawatts every 5 minutes. And it was linear. Usually, when you run a system at scale and you have what we call the calm pattern, and you see spikes, everybody stops, spikes, it means you have a straggler. You find the straggler, the system comes together, you perform. But this was a sawtooth. It was going on like that. And it meant that the GPUs were kind of running out of work, one after the other. So we were looking at different matrices, how to position the job. And ultimately, we got the team together and we're like, okay, guys, it's something we've never seen. It's something different. And I want to, Kim McMahon on our team, who's one of our rock star MPI engineers, she started digging into it, and then she with the rest of the team, and she's like, hey, how about we flip that? Yep. And then the system got there.
And you went from 600 to 900.
Because that was only 8192 nodes. Because at the time, there were a number of racks that we had kind of broken out from the big system to do other tests. Yep. So they had different firmware versions, they had different, all sorts of different settings. But what was beautiful, so that was on May 26th, that Kim had the haha moment, and Kim and the team had the haha moment. And then all of the team, we started a Teams call, and we brought up all of the engineers kind of came together. And what was great is that, okay, we need to flash that firmware, and then one of the guys would pick it up, okay, we need to remount luster there. And it was, by that time, the team was like an engine. It was like gears that were all clicking together. And within a matter of 2 to 3 hours, we basically rebuilt the system, we reintegrated all of the racks that we had forked out, we rebaselined it, and then we told Kim and the performance team, all right, test the fabric, like green light, fabric is good. We almost made it on May 26th. We failed in the backsolve of the run. We were at 95%, and then the backsolve failed. And then we had a few tries during the night, and then I remember, many of us that night didn't sleep much, and I remember kind of somewhat waking up at 5 in the morning, and I'm still in my bed on my phone, tailing the run on the logs, looking at the power curve, and it's good. And I go on Slack, because we had a big Slack channel. I'm like, oh, this one's looking good. And then Scott's like, Nick, don't jinx it. And then it's coming. And after the end of the run, right, we call that the tail. And then like the tail is looking like it's going to end over an exaflop. And then the number comes out, and then you need to pass the residual test, meaning that the run needs to be precise. And that was one of the most numerically accurate, precise run that we did on the system. So I'm literally 6:15, May 27th, I'll remember that, 6:15 a.m. My whole life, I was literally jumping my bed crying. I'm still emotional about it. So it was, it's an accomplishment of a lifetime for many of us.
Justin shared that he had the screens up at his house, and his whole family was watching him.
Yep. Yeah, we had the dashboard. Everybody loaded up the dashboard.
Yeah.
And then all of our families were like, oh, it's looking good now. So it was, I can talk to my family, but I think it's true from all of us that kind of lived at Oak Ridge. We had, it's not just the team, it's all of our families and that supported us.
And of course, I'm referring to Justin Witt, the project manager for Frontier. And I know after the backsolve, was there one more test after that you had to get through? So
you need, what people, sometimes people, it's called a residual test. You need to, basically a LINPACK run will test for numerical accuracy. And the way I explain that to people that are not in our field, they're like, oh, how come that can be, aren't supercomputers always numerically accurate? And it's like, well, you're dealing with silicon. And the best way to explain that is, remember your math class when you were in high school and your teacher said, when you're doing calculations on your calculator, make sure you keep all the digits after the decimal. Well, imagine a supercomputer that's doing a billion calculations per second. If there's only one bit that flips, the error will multiply really fast. And that's why when you do a large-scale LINPACK run, it's not just about getting the number, but it's also testing it to make sure it's numerically precise and basically validating that you really got the right answer. And on that run, it was one of our best runs. And so we were really celebrating. It was amazing.
It's a great story. So speaking of the LINPACK run, you did, official one was 1.102.
Yeah, 1.102.
And that was out of about 1.7, 1.69 peak. And I think you have some thoughts about that on that limb pack efficiency. It's 65%, and your thoughts on how it could be higher.
So remember, I mean, when the list, it goes the other way in this case, but the peak is numerically, it's basically a mathematically calculated equation. Mm-hmm. So in this case, you look at the GPUs have 220 compute units times 0.8 gigahertz times 256 flops per core per clock, and and then you multiply by the number of GPUs, and then you add the CPUs, and that's giving you the peak number. So you do the ratio. However, what you really want to look at is how efficient are you at the node level, like individually, because what you want to compare is weak scaling to strong scaling. So at the node level, what you're looking at is, of all of the run ended up being on 9248 nodes.
9248.
Out of the 9248 nodes, there's a distribution, right, of the node performance taken individually, and always the slowest one of all of them is actually going to be the last one to come in the Bay Areas during the run. If you look at this and you basically do a limb pack efficiency from multiplication of the individual node performance times the total number of nodes versus the strong scaling run, the system is actually 85% efficient. And I think that's a more accurate measurement of the fabric efficiency. The other way to look at it is when during the first part of an HPL run before the tail, Frontier was actually running at 1.4 exaflop, and we were monitoring the fabric. There was no back pressure. The fabric was just kicking it. And the reason for that is really because, in a way, well, one, the slingshot fabric performed, but two, HPL doesn't stress the fabric that much, and we kind of proved it again, even on an Exascale system. So I'm not making the point for building lightweight fabric. Slingshot's plenty capable fabric, and I think for applications in general, we need to build great capable systems. But in this case, the real way to measure the efficiency actually leads to an 85% efficiency on that.
Do you see some headroom to increase the limb pack score? And would you grab some of the other? Would you have a different configuration? Would you add some of those other nodes back in? Maybe.
We could.
You could, yeah.
But honestly, this is a system that, if you ask my own personal opinion, this is a system that was designed for science. Already on some of the ECP apps, we're seeing over 100x improvement, and that's what that system has to be, used for. And just the power that goes in that system, I think it should be used to run science rather than
And speaking we just mentioned, speaking of power, it did very well on the Green 500 as well. The Frontier, along with its companion system 1 and 2, when they debuted on the list,
came out,
still have a significant showing on the current list. Six or seven HPE systems in the top 10 on the current list that came out here at the show. You hit that DARPA target that got set, 15 years ago, came in under that 20 megawatts at Exascale.
So we did basically 1.102 exaflop and 21 megawatts.
Yep.
So we're just slightly.
It's like 19 point something.
Yeah. We had honestly, that's a target. I've been working in Exascale through Path Forward and all of that and the research for over a decade. I never thought we'd hit that target. That was the one I was like, we're never gonna make it in 20 megawatts. So when it came in,
not the first one,
and then within the hour, I actually I'm like, oh my God, we made it in 20 megawatts. So that was a great outcome.
You benchmarked for the HPCG this year, the High Performance Conjugate Gradients benchmark. A ranking that measures data movement, notoriously low efficiency of peak. It's just how it is. The top one's 3%. The second one is 0.8%. Thoughts on the importance of HPCG, stressing data movement, if design direction should move in a direction that would be higher.
So I mean the Japanese systems, right? Like at Riken, and the Japanese have always built more fabric-rich systems, and that goes all the way back to the Earth simulator. And I think it's basically a different design point. There are tons of arguments in the community about the trade-off there. It's almost like you try to you put two geeks and around beers and you debate around VI and Emacs. I mean, it's both points are actually
less
valid.
filling, tastes great.
Yes, exactly. I think, look, if you look at Frontier, you really want to look at the performance of the apps, and it actually really pays out. But really it pays out because a lot of the work that was done on the ECP, it's all about overlapping compute with communications. If you're able to do that, you're going to be using your interconnect very efficiently for the flops you get. And so far, right, the application community and the scientific community has been able to keep improving the application. So although as a system engineer, I'd like to build systems that are more capable, that have always richer fabrics. So far, I mean, the scale up, the speed ups we're getting on applications, even the flops to interconnect bandwidth ratio, the flops is skyrocketing. It's kind of proving that we have still room to improve our apps and crank out the most out of it. So.
Yeah, as you pointed out, even we love to talk about the hardware, but it's all in service to a greater mission, which is the science and solving some of the grand challenges of humanity. Another way that you're working on that is through this Internet of Workflows that I've heard you talk about. Could you talk about your vision for Internet of Workflows and what HP is doing to bring that to fruition?
So, I mean, really, people are like, okay, what comes after Exascale? And I'm not gonna say the Z word this morning. I think really what comes after Exascale is we think it's kind of a systems of systems. You look at the operating model that we've been having in the high performance computing for like forever. It's really like kind of an island. With almost like an air gap security around the system. So for anyone to compute in a supercomputer, you log in or you VPN, you upload your data, you do your compute. Once you're done, you kind of egress out. Let me give you a great example that I think as a community, we're headed. There's a group that's in San Diego, led by San Diego Supercomputing Center, that's called Wi-Fi. What they do is that they have infrared and visible cameras on airplanes that are flying over California to basically detect ignition, to detect if there's a fire that may happen at any point in time. And I mean, I know you're from California, so
I'm from San Diego.
Yeah, so for people, that's a very critical workload. And what happens is that when it detects ignition, that's like intelligence at the edge, if you will. That's in this case, it's on an airplane. It tells the pilot to kind of fly around to capture more video. But what's really interesting is that then it sends all of the data, the temperature, the wind, the video feeds to San Diego Supercomputing Center, and in real time, they basically compute fire propagation models for like 15 minutes, 30 minutes, 45 minutes, an hour, because they've built a whole model of California, and for every acre, they know the amount of fuel, and fuel in this case is like either woods or houses or things like that, and they've modeled the level of drought, the wind, the temperature conditions, and with that, they're able to build that model and tell the fire chief, the local fire chief, hey, here's what the fire will look like in 15 minutes, and 30 minutes, and 45 minutes. And so the local authorities can go, okay, if we can get to the fire within 15 minutes, we'll be able to contain it like that. If we can't get there before 45, we need to call the C-130s, or basically the big stuff, to try to put it out. And for me, that's one of the most vivid example of the Internet of Workflows, which is coupling data feeds that are coming in real time with supercomputing models to actually have a real outcome on people's life. And I really think that's where we're going next. It's all about coupling exascale supercomputers and smaller ones together with sensors, and then producing real-time output. In this case, to save property and people's lives.
Yeah, that's a great example. And shout out to the lead there, Ilke.
Yeah, Ilke and the team there. It's great. I mean, you hear the story from how they work.
Look it up, and and living there, it's just so important. And that's just one example, And the time that we're living in with the climate change and everything, we really need these solutions and direct impact on
forecasting storms,
on our life, our property, our economic situation. So sure, there'll be lessons learned to carry over to other grand challenges. So here we are at SC22 in Dallas. It feels like back to the usual times of SC.
I think we're all happy to
yes, there's a lot of excitement, enthusiasm, energy, activity, great conversations, meeting people I haven't seen in quite a few years, including yourself. So what are some of your SC highlights here, or other memorable SC highlights, or just how you're finding the event here?
Well, I mean, look, for us, ISC was still kind of on the smaller side. Obviously, we went to, we had the Exascale run for ISC in Hamburg, but we're kind of still almost partying here with the being in the US. So we're really happy about that. But if you go to the HP booth, it's all around the spaceborne and how a computer and how we're going to go to moon exploration.
Speaking of flipping bits.
Yeah, exactly. There you go. So, and ultimately, what we're really looking at, and what people are telling us is, capability computing. People are looking for ways to really consume it on demand, and people want to burst for capacity, but a lot of folks are also coming in to burst for diversity, because a lot of our community will still build supercomputers on-prem that may be of architecture X, Y, or Z, but they're like, yeah, but we'd like to run on that AI accelerator when we need it, or that GPU accelerator when we need it. So at HPE, we're working with the community to look at, and it's coupled with the Internet of Workflows, but basically meta orchestration between sites, and also providing that on-demand capability computing to our user base. And we're talking to our customers with that. We're not going full press release about that yet, but you can see how the Internet of Workflows vision is gelling with some of the stuff we're working in.
So it's this holistic vision from the top supercomputers to the Internet of Workflows, to the cloud, and ultimately enabling all these different kinds of workflows, whether it's the high end or the
It's kind of a rebirth of the grid, right? Remember the grid back then, like over a decade ago.
I'm even hearing the word federation again.
Yeah, so it's federations of systems, and that's the I think that's the way forward, because there's such a diversity of silicon and software, and now workloads, and the workloads. It's not just doing modeling and simulation kind of in isolation. It's coupling it with machine learning models. Think like you might have radio telescopes that will have data that's being fed in and then being pre-processed by a DSP, and that's then fed into a simulation model. That simulation might be steered by machine learning. Yeah. All of those are all now
throwing some optical photonics in there.
Yeah, well, that's as you know, we've been working quite a bit on that. That's definitely part of our future. And by the way, that's also the way to build highly capable supercomputers, and we're going to see more and more optics into our systems in the
so much more we could talk about. We're going to save it for next time. Nick, it's been great talking to you, and thanks to everybody for watching. See you next time.